Hi everyone, welcome to this session, and I will present the work that I did during my postdoc at Queen Mary University, and how to train your robot, teaching robot behavior using Teleoperation. So I start presenting myself. I'm Claudio, if you didn't get it, and I'm a machine learning applied scientist at Amazon, where I commit to be sure that you receive your packages, and sometimes I take it to the letter, delivering them myself sometimes. But I do mostly time series forecasting for volume demand at the moment. However, I am a PhD in robotics AI, and I've been working mainly on activity recognition for assistive robots, robot learning from demonstration, that is what you see here, and in the past also in biometrics. So the problem that we wanted to solve in this project, it was that the robots are dumb, well, literally. So we have a huge demand for automation in the light manufacturing industry, but the robots are neither dexterous enough or smart enough to perform very complex tasks, and at the same time, they are not ready to be in a human-enriched environment. So accidents are a problem, right? So what we want to do is to create a platform that allows you to program the robot without having too much technical skills. So just showing the robot what it needs to do. And this is the solution that we came with. It's a project that's called MenQ, and it was called in my research team. It was CRISP, Ocado Technology, DeepMind, and Shadow Robotics. And what was the solution? It was to provide image of what the robot sees to the human through a VR headset, teleoperate the robot using your own hand, so the robot will copy your movements of your hand, and to provide some feedback, so to understand, so that you can feel what the robot does, we will provide haptic feedback using tactile sensing. So we will connect the tactile sensors on the robot hand to a haptic device. By doing so, we can create a set of demonstrations that we can use to program your robot in a smarter way, let's say. So this journey started with very cheap sensors and devices, and this was my approach for finger control using lip motion. And the mapping here, it was very simple. I was just mapping the fingertips to the fingertip of the robot. It is working decently well, but then we discovered that mapping directly the joint angles, it was better, right? Just because the robot hand and the human hand are significantly different, more than you will imagine. On the other hand, we developed this very cheap glove. We built it ourselves, and it's just a glove that you can buy in a shop, where we attached vibrators on the fingertips, and any activation of the sensor on the robot hand will correspond to a vibration on your hand. That said, it's very basic, but it works well enough. We will see later. And finally, the arm teleoperation was working with two modalities. One was using my hand, so I could move my hand forward and backwards, and the robot hand will move forward and backwards. But since you don't want people to get out of the workspace of the lip motion, because weird scenarios happen, you want to use the keyboard for larger movements, so that just to be safe. And yeah, this is more mumbo jumbo for technicians. So we tested first this approach using a virtual environment with virtual objects and doing very simple tasks like grasping, holding, and manipulating the virtual objects. It proved to be nicely working, or at least nicely enough, and the haptic feedback was actually helping significantly the success in the demonstrations, in performing demonstrations. Then we moved to actual things and did with the actual robot, which is a bit more interesting than the virtual stuff. And we built this data set of demonstrations using fruit items. This was the simplest one, the blueberry box, and we're having demonstration with single items, so in this case in a box, or clutters. So you will have to declutter the environment and then pick up because you don't have space to put the chunky fingers of the robot. And the banana was particularly hard, I tell you that. I don't want to stick you for all the demonstrations, but the last one is an avocado. So what we were trying to do is, let's try to split these very long demonstrations in sub-skills that are much easier to reproduce. Because if you try to do any behavioral cloning, you have a lot of drift problems and such and such. But if you have very short skills, it's much easier to reproduce. So what we were doing is segmenting these long horizon tasks in separate skills that we can learn primitives of. So how do we do it? We decided to do it without vision. We wanted just to use kinematic data, so the robot state, what is the configuration at the moment, and the tactile data. Obviously using a window of time for the sensing data. Very simply classifying each single time step and saying at this time this activity is happening. Oh, sorry. So this is the stuff that I did 2 years ago as a postdoc there. I'll show you something a bit newer. So we moved to a different configuration that is a bit more expensive and also more accurate than the one that I was using. And that enables us to do something a bit more interesting. So we actually managed to integrate the virtual reality visor, and we were using this other haptic device that is providing actual force control, so you can really feel the sensing of the tactile. We also changed the tactile sensor and such. But the cool thing is not that we improved the teleoperation, but also we are able to do blind teleoperation, so no vision, we don't see anything. But we're able to reconstruct the item with just the tactile data. So we touch, and at some point you get more or less what is the shape of the item that you're picking up, which is neat, honestly. And this is something that comes from last night, because we submitted, so please don't photo this. We submitted this extension of the previous work of classification, where we are doing, we developed a data set of skills that are very small and very well-defined, and we use them to segment a lot of long horizon tasks. All of these skills are presented in a dataset like individually, so literally grasp, literally push, this kind of thing. We are able to detect them very, very accurately in very long demonstrations. And we already demonstrated that they were beneficial to replicate the same long horizon tasks. And pretty much that's it. Sorry if I was too long. And here are some contacts if you want to.